Good afternoon, everyone. We'll just wait for I think 3 to 4 minutes, and I think we'll be ready to go. Just waiting for a couple of more minutes, waiting for other students to join in, and then we can start with our live session. Just waiting for 1 more minute, and I think we can begin. So let's start. So before we proceed, we are bound to give our introduction every time. So good afternoon, everyone. My name is Musa Rafiq. I'm your course TA. The course is Digital Circuits that is taught by Professor Shantanu Chattopadhyay from IIT Kharagpur. I'm a PMRF student from Department of Electrical Engineering at IIT Kanpur. We carry out this TA work every week as a part of our PMRF deliverables. So this time I'm the course TA for Digital Circuits. This is live session number 6. So in this session, we'll be discussing the problems pertaining to the materials from week 6 itself, mostly from the sequential circuits part. And other than that, regarding the rules and regulations of the live session, they are pretty similar, but I'll just reiterate them. First of all, your microphone should be turned off, and also video should be turned off. After I have solved a problem, ample time will be given to asking your doubts. Try to write in your doubts in the chat box. If not, you can unmute yourself and ask your doubts. And during my lecture, I keep at least 4 to 5 problems such that I ask you guys to solve them first. I usually give 3 to 4 minutes to the students to solve them. Afterwards, I'll show the solution to those problems as well. And even during the course of a live session, you feel like you have some doubt pertaining to previous problems that you have solved. At the end, I'll again give you time to ask me your doubts related to that. So let's begin this live session with the first problem that we have today is. So the problem that we have today is first problem. It states that which of the following circuit, and also I would like you guys to also, when I'm asking you some questions, some queries, to please be attentive, responsive. In that way, the class is gets much better. Yes, I want it to be more of a dialogue rather than a monologue. Anyways, so question number one: which of the following circuit can be used as series to parallel converter? So the task at hand is we have to figure out which of the following circuit can be used to serial to parallel converter. So what I'll have here is I'll just assume I'm having some circuit. I'll call it a black box, right? And here I am having series input. This black box will be such that I'll be having parallel outputs, right? So in general, we can say that we have a signal which is called as common source line, which is, let me just, I don't know what I have done. Yeah, common source line, and it goes to a circuit such that we have switches in here, and these are our parallel outputs, and there are control signals, let's say A and B. Based on the value of control signal, the output gets routed to one of the input gets routed to one of the output lines. So looking at this thing, can you tell me which one of the following circuit can do this functionality? You have read it very well, so you might be knowing this. Which one of the circuits will do this functionality among the following? You can type in your option if you want. Yes, thank you. So this will be your demux, right? So in demux you have your input line, and then you have your mux, demux, then you have your output lines, and here you will have your select lines. Control signals are your select lines, a common source line is your input. So this was a pretty straightforward question, and the answer to this question was demux, right? Now let's just move to question number two, sorry. It states that PLA consists of, so PLA stands for programmable logic array, right? So it consists of, so what does it consist of? Anyone in the audience? PLA, that is programmable logic array, consists of, among the following option, what does it consist of? No. So PLA, that is programmable logic array, consists of programmable and programmable OR arrays. C, it's C. Both are programmable and as well as OR. I think you got confused with PAL, I think. Anyways, you can refer to your lecture notes if you have some doubts. This is pretty simple question. Now, this was my first question. Then I had question number two. Right now, another question uh, that I'd like you guys to solve first. I think you can give answer in real time as well. So we have the SR latch is an example of A, combinational circuit, B, synchronous sequential circuit, C, 1-bit memory element, D, 1 clock delay element. So anyone, what is SR latch example of among the following options A, B, C, D? No, only one is the correct answer. Among following options, only one of the options is correct. It is not multiple answer. Only one option is correct. Anyone else? So, whenever you hear of a latch, latch is the one of the most basic memory element. And whenever we talk of an SR latch, it is an example of one-bit memory element. So this is a basic memory element that you have in your digital circuits. That is your latch, right? So whenever you think of a latch, think it like a one-bit memory element. That's all. Now I have a question. So this states that a JK flip-flop with J equal to 1 and K equal to 1 has a 20 kilohertz clock input. The Q output is, so we have a JK flip-flop and we are given the input clock frequency, and then we need to figure out what will be the output clock frequency given that my inputs are J equal to 1, K equal to 1. So before we proceed, so what we have here is we have a J, K, and we have a clock, and my J equal to K equal to 1, and this is my output. This is my clock. So this is J, this is K, this is clock, this is J, this is K, and this is Qn plus 1. So when clock is 0, I don't care about the inputs. When clock is 0, I don't care about the values at the input. Can anybody tell me what will be the output Qn plus 1 equal to? When J equal to 0, when clock equal to 0, my Jk is having a don't care condition. What will be Qn plus 1 equal to? No, inputs are don't care. I don't care about the inputs. Output will be not be don't care. Output will have some value, and that value will be equal to, no, it won't be equal to 0. It will be having output. We call it as no change. By no change, we mean it will be equal to Qn. Whatever the previous value was there, it will be equal to that value, right? It will maintain its state. Now I'm making my clock 1 for all other cases, and I have my cases like this: 0 0 0 1 1 0 1 1. Now can you guys tell me, for the inputs j equal to 0 and k equal to 0, what will be my output Qn plus 1 equal to? No change, right? So this will be again no change, and we term this one as memory. Now for j equal to 0 and k equal to 0, it will be, right? Thank you. And for j equal to 1 and k equal to 0, thank you very much. And finally for the condition 1 1, toggle. And how do we represent toggle as? Correct. Thank you very much. Thank you for your responses. So it will be written as Qn bar. So this will be toggle, right? So I am having my input, let's say clock signal like this, and this is positive edges I'm marking, and my j equal to k equal to 1. That means my output will toggle, assuming my output was initially at 0. Now at the positive edge, what will happen? At this edge, Qn will go to j equal to k equal to 1. Qn is 0. At the positive edge of the clock, what will happen to Qn? Qn equal to 0 will become correct. Qn equal to become 1. Now at this point, will there be toggling? Will there be toggling at this point? No. Yes, because it's a positive edge triggered. Now what about here? Now Qn will go to 0. Thank you. Thank you for your responses. So again, we'll have this and we'll have this. So even if you look at the waveforms, you'll simply see my frequency gets halved. That is my time period doubles. So that implies my output frequency will be 20 by 2, that is 10. In general, you can write output clock frequency, output frequency will be equal to f clock by 2 raised power n, where n is your number of flip-flops, so it will be f clock by 2 raised power 1, so it will be 20 by 2, that is your 10 kilohertz. Units are important as always. So option, what was this? Option D is your correct answer. Now, any doubts in this question? If there are any doubts, you can write them in the chat box. Okay, that's fine. Now, what I'll do, I have marked this question. Basically, I've highlighted this question. That means I want you guys to solve this question first. Write in your answers, not the complete answer, just the correct option in the chat box. So I'll read the question for you. I'll give you a couple of minutes. I think it should not take more than 3 to 4 minutes. So you guys will solve it first. Type in your correct options in the chat box. Then I'll show the solution. So the question reads as, for the clocked flip-flop circuit shown below, what is the correct characteristic equation? So the flip-flop circuit is given below. You need to figure out what will be the correct characteristic equation, right? So it should not take more than 3 to 4 minutes. Then I'll show the solution. So I have one student typing in the answer. What about others? Please also participate. In this way, you will learn much better. And if you make some mistakes, you will remember them for a very long time, and in future you will avoid them. I'll just wait for, I think, 30 to 40 seconds more, and then I'll show the solution. Requesting others to also participate. So now let me just show you the solution. So let's assume clock is 1, right? Now what we have here is we have A going to the AND gate and B going to the AND gate again, and clock is already 1. So when one of the input is 1, so output of the NAND gate will simply be the other input. So let me just call this as A star and B star. When clock is 1, that implies A star is equal to A and B star is equal to B. Now let's just draw the truth table of this circuit. This is your B, this is your A, this is Q, this is your Q complement. So we have A, we have B, we have Q n plus 1. So when A equal to 0 and B equal to 0, when A equal to 0 and B equal to 0, Qn will be equal to Qn plus 1 will be equal to Qn, the previous state, right? When A equal to 0 and B equal to 1, Qn plus 1 will be equal to Qn plus 1 will be equal to 1, right? Because B is 1, so that means Q bar is 1. Q bar is 1 and what should I say? Q bar is 1, right? So sorry, Q bar is 0. That 0 goes to this first NOR gate, and A is also 0, so Q will be 1. Now for 1 0, the output will be 0, and for A equal to B equal to 1 1, my output will be, can anyone tell me what will be my output for A equal to 1 and B equal to 1? Invalid. So invalid is represented by X, right? Now from this truth table I will construct a characteristic table. So how will I construct it? I will write A, then I will have B, then I will have Qn, and then Qn plus 1. So 0 0 0 0 0 1 0 1 0 0 1 1 0 1 0 1 1 1 0 1 1 1. So when A equal to B equal to 0, its memory state Qn plus 1 will be equal to Qn. So 0 and 1. Basically it will follow Qn. For 0 1 it is 1 1. For uh, for 1 0 it is 0 0, and for 1 1 it is invalid. Right. Now I'll draw K map for three variables Which are those three variables? It's A, it's B, and it's Q, right? Qn plus 1 and Q are same thing. So this is A bar, this is A, this is B bar, Q bar, B bar Q, BQ, BQ bar. So this is 1, 1, 1, and then we have don't guess here, right? Now let's see how we can minimize them. So we can construct a chord with this and a pair with this, right? So the term arising from this chord will be equal to B, right? And from this it will be A bar and Q. So that implies Qn plus 1 will be equal to B plus A bar Q, right? Now I have my answer for Q of t plus 1 equal to B plus A bar Q. And also for the condition on inputs, A, B should be equal to what? What is the condition that I have to put for inputs such that this holds? What is the condition on input I'll be putting? A, B equal to? What should the condition on inputs? Can anyone tell me what should be the condition on inputs? As you can see from the truth table, I told that for A equal to B equal to 1, it's an invalid operation. So that implies A dot B should always be equal to 0. By putting this condition, I'm saying never take 1 1 as your input case. So that implies A B is equal to 0. And you look at the options. Option A is your correct answer, right? Any doubts related to this question, that is question number 5? Okay, nice. So now let's just move forward to question number 6 of today's live session, which states that the above synchronous sequential circuit built using JK flip-flops is initialized with Q2, Q1, Q0 equal to 0, 0, 0. The state sequence for this circuit for the next 3 clock cycles is. So we are given the initial states, we are given the circuit, and we need to figure out what will be the state for the next 3 clock cycles, right? So let's just carefully look at the circuit, and this is your 2 for sanity. Let me just number them. This is your 2, this is your 1, and this is your 0. So now what should I say? Your J2, that is the input for this. What is this J2 equal to? If you carefully look it is equal to Q1 bar, right? This thing. And similarly, what is K2 equal to? Can anyone tell me what is K2 equal to? What is K2 equal to? If you look at the circuit, you can tell me what this K2 will be equal to. Q0. Thank you. Similarly, J1 will be equal to K2. K1 will be equal to K2, Q2 bar. J0, what will J0 be equal to? Q1, and K0 will be equal to Q0 bar, right? You can check at your places as well. So now what was the initial state given? It was 0, 0, and 0. So that implies my J2 will be equal to Q1 bar, that is 1. Q2 will be equal to 0. J1 will be equal to Q2, that is 0. K1 will be equal to Q2 bar, that is 1. Again 0 and again 1. Now let's just look what will be the Q2 equal to Q2. Q2 will be depending on J2 and Q2. J2 is 1 and Q2 is 0. That implies, so I'll just draw here. Qn 0, 1, Q bar. So for 1, 0, it will be equal to 1. For 0, 1, that is this. 0, 1, it will be equal to 0. And for 0, 1, it will be again equal to 0. So my next state input will be 1, 0, 0. Now J2 is equal to Q1 bar. Q1 is again 1, 0, so it will be 1. Q0 is 0, so it will be 0. J1 equal to Q2. So Q2 is 1. Q2 bar will be equal to 0. J0 equal to Q1. Q1 is 0, so it will be 0. And Q0 bar will be 1. Now the inputs 1, 0, so it's again 1. 1, 0, it's 1. 0, 1, it's 0. Right? Now 1, 1, 0. J2 is Q1 bar, so it will be 0. K2 is Q0, so it is 0. J1 is equal to Q2. Q2 is 1. Q2 bar is 0. J0 equal to Q1, that is 1. Q0 bar is again, what should I say, 1. Right? Now 0, 0. So previous state will be maintained, that is 1. 1, 0. So it is 1. 1, 1. So toggling. Previously it was 0 right here. Now it will be 1. So after 3 clock cycles, my inputs, my state will be 1, 0, 0, 1, 1, 0, 1, 1, 1, 1, 0, 0, 1, 1, 0, 1, 1, 1, and that is option C. Any doubts, any queries related to this question? If not, we can move forward to the next question of today's live session, that is question number 7. So the 7 is, I have kept it general question because most of the questions, at least expect, I think, one of the question based on these lines, that is a conversion problem. Even if you don't expect any question from this, but from concept point of view, this is pretty important. So please pay attention to this problem. So what does the problem say? It states that convert a T flip-flop to a D flip-flop, right? So what does that mean? We are given one flip-flop, right? We are given one flip-flop and we need to construct another type of flip-flop out of that. So generally, there are 5 points to remember while solving the conversion problem, right? So what are these 5 points? They are tabulated here, they are listed here. Point 1, that is you have to identify your available flip-flop and required flip-flop, right? So you must be given a flip-flop and a question will be asking convert a flip-flop from convert a flip-flop A from flip-flop B. So your B is your available and A is your required. So that is identify the required flip-flop and the available flip-flop here. After that, you have to make characteristic table of required flip-flop. So the required flip-flop, you have to construct a characteristic table. Here it's available and required. Here you have to construct table of required. After constructing a characteristic table for a required flip-flop, you will be making an excitation table of the available flip-flop. And then what you will do, you will write the Boolean expression using K-map or any other minimization techniques. And finally, you will draw the circuit. So basically, first 3 points are important, and out of those first 3 points, you will get the other 2 points. So based on this, The question asks us to convert T flip flop to DV flip flop. Now my question to you guys is, what is my available flip flop? T, correct. So T is available, and that implies my required will be D flip flop. Thank you very much. Now I'm asked to identify. I identified. Now what I have to do, I have to construct a characteristic table of the required flip flop. So the required is D. So this is D, this is Qn, and this is Qn plus 1. 0 1 1 0 1 1. So what will be Qn plus 1 here? Here. What is Qn plus 1? Qn plus 1 is 0 because D flip flop, my output is just simply the input. 0 1 1, right? Now after constructing a characteristic table of the required flip flop, what I am required to do is I have to make excitation table of the available flip flop. So available, I'll just write T and construct the characteristic excitation table. So Qn equal to 0, Qn plus 1 equal to 0, T will be equal to 0, Qn plus 1 equal to 1 and 0, this will be 1, this is 1, and this is again 0, right? So this is the table I got. Now I have to write the output expression for T. So output expression for T between input D and Qn. If you carefully look between D, you carefully look at between D and Qn for T, you can see that T is equal to D XOR Qn. Here 0 0 is 0, 0 1 is 1, 1 0 is 1, 1 1 is 0. So I have made the excitation table. I have written now the Boolean expression. I need to draw the circuit. So this is my T flip flop. This is my input, to which XOR of Qn and D is going. So this whole is my D flip flop made out of made out of T flip flop, right? Any doubts, any queries, please ask. If not, we can then progress to the next question. So I assume there are no questions. Okay, thank you. So now I have this question for you guys to solve first. Then I'll show you the solution to this question as well. The question states that which one of the following circuits converts a JK flip-flop to a T flip-flop? I'll write the question again. Read the question again. Which one of the following circuits convert a JK flip-flop to a T flip-flop? So you are given the four options. Please write down the correct option in the chat box. It should not take more than 2-3 minutes, and I also shown you the methodology how to do these questions just before this question. Yeah. So apply that methodology, and if you have some other method, do whatever is feasible to you guys. Do it and write the correct options in the chat box. So I see some of the students have written their answers. That's nice to see. So let me just wait for some time. I think by now all of you guys have solved it. So now let's just start with the first point, that was to identify the available and required flip-flop. So what is the available flip-flop here? It's JK, and your required T. Thank you very much. Now I have to write characteristic equation of the what should I say, required flip-flop. So that is J K and Qn. So that is 0 0 0 0 0 0 1 0 0 1 1 1 0 0 1 0 1 1 1 0 1 1 1, and ultimately I have this. This is my Qn plus 1. So when my J so before proceeding, always make a truth table for your what should I say, to avoid any confusions. So J K Q N 0 0 0 1 1 0 1 1. It's Qn 0 1 Qn bar. So when J equal to 0, Q equal to 0, it's memory. So it will be 0 1. For 0 1, it's 0 0. For 1 0, it's 1 1. For 1 1, it's toggling, right? Now after that, we are done with the two steps. That is, first was identification, second one was making the characteristic table. So the third step will be writing what should I say, writing the excitation table. Oh, I messed up, sorry, sorry. See, this happens. So available was JK and required was T. So we need to write the characteristic equation of T flip-flop. See, so this is T, this is Qn, and this is Qn plus 1. So it is 0 0 0 1 1 0 1 1. So for 0 0 it's 0, for 0 1 it's 1, for 1 0 it's again 1, for 1 1 it's 0. Right. Now I have to write the excitation table for J and K. So when Qn and Qn plus 1 is 0 0, let me just write the excitation table here first for JK, then we can plug those values there. Qn plus 1 JK 0 0 0 1 1 0 1 1. So it's 0x 1x x1 x0. Now Qn equal to 0, Qn plus 1 equal to 0, so it will be 0x. It's 1 1, so it will be x0. It's 0 1, so it will be again so it will be 1x, and for 1 0 it will be for 1 0 it will be for 1 0 it will be x1, right? So this is my complete table. Now I'll minimize the output. So this is what should I say, this is J, this is K, so this is T, this is Q for J. So it will be equal to 0x 1x. That implies J is equal to Q, J equal to T. And for K, this is T, this is Q, this is x0 x1. For K also it will be equal to T. So J equal to K equal to T will make the JK flip-flop a T flip-flop. So that is option A, as rightly pointed out by the students. So the mistake I had made, what I did earlier, was I wrote the characteristic table for the JK flip-flop, which was the available flip-flop. That was the mistake I made. I had to make characteristic table for the required flip-flop, that is T. So I have to make characteristic table for the T flip-flop and then the excitation table of the available flip-flop, that is JK. And ultimately I wrote the Boolean expression for J and K in terms of T and Q. So it came out to be J equal to K equal to T. That is option A. Any doubts? So this was question number 8 of today's live session. Now question number 9 asks us how many flip-flops are needed to divide by 16. So how many flip-flops are needed to divide by 16 basically means modulus of the circuit is 16, and if we have n flip-flops, right, if we have n flip-flops, we know modulus should always be less than or equal to 2 raised power n. That implies 2 raised power n is greater or equal to modulus. That implies 2 raised power n is greater or equal to 16. That implies n should be greater or equal to log to 16. That implies n should be greater or equal to 4. So we need at least 4 flip-flops divided by 16. Now question 10, we have here is a programmable logic array is given, and we need to find out the Boolean function f implemented by the PLA. So what I will do here is I'll mark these outputs first coming out from the NAND gate. This is F1, this is F2, and this is F3. So F1 will be equal to F1 is equal to P bar here, Q bar here, and R. So it is P bar, Q bar, and R. F2 is here, so it's again P bar, then it's Q, then it's R. So it's P bar, Q, R. And finally I have F3, which is equal to this line, P, Q bar, and R. P, Q bar, and R. So what is my F equal to? What is my F equal to in terms of F1, F2, and F3? Anyone? What is my F equal to in terms of F1, F2, and F3? Thank you. So F is equal to F1 plus F2 plus F3. So my Boolean function implemented by this PLA is P bar Q bar R plus P bar Q R plus P Q bar R. Now this is the question I would like you guys to solve first, then I'll show the solution. So a 1 megahertz clock is applied to a JK flip-flop where J equal to 1 and K equal to 1. What is the frequency of flip-flop output signal? So you are given the condition for inputs with clock frequency equal to 1 megahertz. You need to figure out the output clock frequency. Anyone else? What is the answer? So the answer to this is option B, as rightly written by Abhishek. So we saw this question earlier as well here, right? When your j equal to k equal to 1, that is the toggling condition is given, and you have the input clock frequency, your output clock frequency gets divided by 2. F clock is equal to f by 2. Sorry, f output equal to f clock by 2. So what we have here is f of output is equal to f clock by 2. F clock is 1 megahertz divided by 2 equal to 0.5 megahertz, that is equal to 500 kilohertz. That is option B, as rightly pointed out. Now to the question 12 of today's live session. It states that what does the following flip-flop configuration does? So it should not what do, what does. So what does the following flip-flop configuration do? So we need to figure out this configuration that is given. What is the working of this configuration, right? So I have clock cycles written here: one, two, one initial, so first, second, third, and fourth. D equal to q bar. Let's just assume q equal to 0. So that implies q bar. So let us assume first one was d equal to 1. First one was d equal to 0. Let's just make an assumption d equal to 1 or d. Anyways, you can make any assumption. So first one was d equal to 0. So we'll write 0 here. What will be qn plus 1? Qn plus 1 will be 0 and qn plus 1 bar will be 1. How am I writing this qn plus 1 equal to 0? Can anyone tell me? How did I arrive at this conclusion? Qn plus 1 equal to 0. What I did, I made an assumption that first d equal to 0. Then yes, correct, because the output qn plus 1 is equal to d. So I have written that. Now qn plus 1 is 1, so it will be 1, it will be 1 and 0, then it will be 0, 0 and 1, and it will be 1, 1 and 0, and it will be 0, 0 and 1. What is happening? This is changing state: 0, 1, 0, 1, 0, 1, and so on. And this one, output 0, 1, 0, 1, 0, 1. And can you tell me what this is? I have output which changes from 0, 1, 0, 1, 0, 1, 0, 1. What is this? Yeah, it is square wave, but based on the input, what it is? Sorry, based on the options, what it is? Yes, it's a 1-bit counter. Correct. So this was question number 12. Now I have question number 13, which I want you guys to solve first. Then I'll show the solution. It states that the output of the circuit shown below will have the frequency as. Basically, you need to find out the output frequency. So do it, then I'll show the solution. So let's just identify. So basically there are three flip-flops. So your n equal to 3 and they are toggling. How I am saying they are toggling? Because t equal to 1, right? And my clock is 1 kilohertz. So f clock is 1 kilohertz. That implies f of the output will be equal to 1 kilohertz by 2 raised to power 3. So it is 1 by 8. So it's 0.125 kilohertz. 0.125 kilohertz is equal to 125 hertz. So option A is the correct answer. Hope this is clear, right? Now, coming to question number 12, 14 of today's live session, it says that a mod 2 and mod up 5 counter when cascaded together. So a mod 2 and a mod 5 up counter when cascaded together results in a mod dash counter. So anyone, what will it result to? So when you cascade a mod 5 up counter and a mod 5 2 up counter, what will be the to cascaded together results will result in what mod counter? Anyone? So basically when you cascade a mod 2 counter, so the ultimate mod will write by mod m will be equal to mod m1 multiplied by mod m2, that is 5 multiplied by 2 and it will be 10. So the final will have 10 as its required answer, right? Now question number 15. These are pretty simple questions and that's why I want your engagement as well for these questions. So question number 15 asks us the output of a JK flip-flop with asynchronous preset and clear inputs is 1. The output of a JK flip-flop with asynchronous preset and clear inputs is 1. The output can be changed to 0 with one of the following conditions. By applying J equal to 0, K equal to 0 and using a clock. By applying a J equal to 1, K equal to 1 and using the clock. By applying J equal to 1, K equal to 1, 0 and using the clock. And by applying a synchronous preset input. So which option do you think is the correct answer? Yes, option B. By applying J equal to 1 and K equal to 1, I'll be able to change. So by applying J equal to 1 and K equal to 1 and using the clock, I'll be able to change the output from 1 to 0, that is toggle, right? Now I have this question for you guys to solve first, then I'll show the solution to this as well. So the question states that two D flip-flops are connected as synchronous counter that goes to the following QBQA sequence. That is, the sequence is 00110110. The combination of inputs DA and DB are, so you need to find out the combination of inputs DA and DB. Given are the four options, please type in your correct answer, type in the correct option in the chat box. I'll give you 3 minutes to solve this. Anyone? Has anyone solved it? So let me just wait for other people to also type in, and then I'll show the solution. So okay, let's just draw a table here that has QB, QB, then QA, QB plus 1, QA plus 1, then we have DB, and then we have DA. So it's making the transition from QB QA is equal to 0 0, then 1 1. So without writing, so QB QA is 0 0, right? Then my next state is 1 1. So I'll write 1 1. Now QB and QA are 1 1, and my next state is 0 1. When my next state is 0 1, then it's 1 1 0 1, then it's 1 0, and when it's 1 0, then my next state will be 0 0, right? So based on this, can you tell me what is dB equal to here? At this point, what will be dB equal to? So in the earlier questions, you guys told me that dB has characteristic equation dB equal to QB plus 1. Just for QB plus 1 equal to dB. So what will be dB equal to here? Look at the table. You guys should be able to tell me this. What will be dB equal to? No, no. It should not be 0. It will be 1. QB plus 1. QB plus 1 equal to dB. Right. So this will be 1, 0, 1, 0. And what is dA equal to? What will dA be equal to here? 1. And here? Here? Right. Now dB will be equal to between QA and QB. So it is that implies dB is equal to QB. Now for dA, so I'll have QA, QB for dA. So it is 1 1. So dA is equal to QB complement QA complement plus QB QA. So that implies dB is equal to QB and dA is equal to QB bar QA bar plus QB QA. That is option D. That is the correct option. Right? Got it? Now, coming to question number 17 of today's live session. So, you guys tell me what is the feature that distinguishes the JK flip flop from the SR flip flop? What is that feature among the following options? Yes, toggle condition, correct. So now question number 18. A 4-bit counter is used to count from 0, 1, 2, so on up to n. The value of n is, what will be the value of n? B, 15, correct. So we have, let's say, a n-bit counter. It will count from 0 to 2 raised power n minus 1. Here n is equal to 4. So it will count from 0 to 2 raised power 4 minus n, that is 0 to 16 minus 1, that is 0 to 15. So it will count up to 15. 3 T flip-flops are connected to form a counter. The maximum possible state for the counter is, how many states are possible? Correct. That is 2 raised power n, 2 raised power 3, that is 8. The state transition of a T flip-flop from 0 to 1 requires, I think we did this type of question, but still, this is in different form. You guys can tell me. The state transition of a T flip-flop from of T flop from 0 to 1 requires 0 to 1 requires. I have 0, it requires from 0 to 1 requires. If you give 0 at T input, it will be 0, right? Yes, it will be 1 at the input. See, this is Q, this is T, this is Q, and 0, 0, 0, 1, 1, 0, 1, 1, and output will be 0, 1, 1, 0. You have 0 state and you need to make transition to 1. So you will have 1 at the output. Sorry, 1 at the input. Now this is the last question of today's live session. This is a question I would like you guys to solve it first, and then ultimately I'll show you the solution. I'll read the question for you guys. The truth table for XY flip-flop is shown below. Design the flip-flop using JK flip-flop. So you need to design a XY flip-flop using a JK flip-flop. It's again a question based on the conversion problem. So solve it and then I'll show the solution. I'll give you 3-4 minutes and then I'll show the solution. Has anyone done it? I'll just wait for 1 more minute and then I can show you the solution. So let me just show you the solution. This is based on the conversion problem. So 5 points I told you to remember. So first of all is to identify the required and available flip-flop. So if I ask you what is the available flip-flop here, available flip-flop is, yes, so the available flip-flop as rightly pointed out is JK, and what is the required? It's XY. So point number two is write the characteristic equation, characteristic table, or draw the characteristic table for XY, that is the required flip-flop. So it is X, Y, Qn. 0 0 0 0 0 1 0 1 0 0 1 1 0 0 1 0 1 1 1 0 1 1 1. And here I'll write Qn plus 1. So when x equal to 0, y equal to 0, my output toggles, so it will be 1 0. When it's 0 1, it's 1. When it's 1 0, it's 0. And it's 1 1, it again toggles, so it will be 1 0. Right. So in this way we are able to construct a, what should I say, characteristic table. Just give me a second. Give me a second. So in this way, let me just write 0 1 will be 1 1 0 will be 0 0 and 1 0. Now we wrote the characteristic, we drew the characteristic table for xy. Now we need to write the excitation table for jk. So excitation table of jk, let me just draw here as well. Qn plus 1 jk 0 0 0 1 1 0 1 1. It's 0 x 1 x x 1 x 0. Here I have 0 1, right? So it will be 1x. Then I have 1 0, that is x1. Similarly, it will be 1x x0 0x x1 1x and x1. So now what we need to do is write the expressions. Let me just write the expression for j first. So this is x, y, and q, and this is for j. And the truth table will be like 1 x x 1, then 0 x x 1. So we can construct a chord on this. So j will be equal to x bar coming from this, and from this I will be getting y, x bar plus y. Now construct a k map for k. This is x, y, q, and this is k. It will be x1, 0, x, x1, 1, x. So it will be this and this. K will be equal to x plus, and from here it will be y bar. So that implies j is equal to x bar plus y, k is equal to x plus y bar. That is option D, as rightly written by one of the students. So this was all for today's live session. That was the live session pertaining to week 6 material. If you have any doubts, any queries, please let me know. Otherwise, we can close the live session. If you have any doubts, queries, please let me know. Otherwise, you can close the live session. Thank you for joining, and thank you for being responsive at the same time. This was a really good session. Hope to see you next time. I think next time we'll meet on 8th of September from 3 to 5 p.m. and we'll be discussing problems related to week 7 material. Thank you guys. Thank you for joining.